Okay, we're happy to have Tao Han from University of Pittsburgh, founder of PitPac, former Davis professor, former chair of BPF, and many other things to tell us about the muon collider.
No, John.
Welcome back.
Muon collider is only the side part, right? So in any case, I was asking John, there's so interesting topic to discuss, and he picked up this one. So the first part, okay, so some of you may have not been to Israel. So this is our campus. So this is the cathedral for learning, and it's the tallest education building in the US. So it's pretty high.
Ivory Tower.
Yeah, so this is fantastic. Of course, I have the fond memories. And yesterday I walk around, yesterday evening I walk around the town, and it's always so enjoyable to visit Davis. So there are two things I want to discuss today. So this was John's choice. I want to discuss this the electroweak sector is basically including the Higgs, and we think that we have a complete standard model in the electric sector already. But in fact, if you think about this, what the electrophysics, including the Higgs sector, will tell us if you think about a high energy limit. So it will be very interesting, and many things are not quite settled. Just similar to the QCD. In the QCD case, you seem to have a very well-defined Yang-Mills theory. But at any different energy regimes, the very low energy, confinement, high energy, and the asymptotic freedom, and so on and so forth. In fact, if you look at it, that's quantum field theory. And quantum field theory tells you this not only just one mathematical formalism, but at different energy regimes, the phenomena may look very different. So my question is, what about this electric sector at a rather high energy regimes? That part is relatively theoretical, but I think they're very interesting. I want to share this with you. There are still unsolved issues we need to continue to look at. It so happens nowadays we'll talk about the high energy the collider options with the FCC, the future circular collider at CERN, the hadron collision option that will lead you to the partonic central mass energy about multi-TeVs. And the recent discussion about the high energy muon colliders will also lead you to multi-TeV region. It so turned out that our early studies along this electric sector at high energies may have some applicability along these two machines. So that's the second part. Second part is that I want to show you that what may be the is it rather dark? Is it bright enough?
Okay, it's okay.
Doesn't really show up.
We could close one more.
Is that the one I can use?
Sure.
Yeah. I will probably use this one. So I want to apply this high energy electric physics to the future collider to see what phenomena you may be able to see.
Yeah.
Is that probably slightly better?
It's visible. Yeah.
Okay, good. So these two parts may not be that coherent, because the first part, actually, we started this even way before the high energy muon collider was contemplated a couple of years ago, when we thought it was academic. It was very interesting, and we learned. But it so turned out that some of these calculations be very applicable to the high energy collisions, both the hadronic and as well as the muon collider. So that's the two things we put together. We have been working on this for a while, and this one was the first one to lay out the electric sector in 2016. And some of the later ones I work with our students and postdocs, and those are the electric sector, and those are the new physics. Something like what dark matter may look like, what the Higgs precision measurement may look like, and at the high energy muon colliders. So that's a two-part. So that's the thing about why this is interesting. And let's look through some numerology. So I'll give you quite a few examples. Look at the energy versus the vacuum condensation. So if you think about this electric vacuum expectation value, this quantity is about 250 GeV. We knew this even ever since the beta decay. So ever since the beta decay, we know there's a weak interaction, and weak interaction is set by this energy scale. So that's the electric scale, vacuum expectation value in the Higgs sector. If you look at this, the ratio here, think about the energy. At the low energy around the nuclear physics, for example, that's where the beta decay is, and then you see this dimensionless quantity is really G Fermi times the energy scale. This is basically governed by the W mass and take mass A. That's why we call this weak decay, weak nuclear decay. But in reality, it's not really because of weak interaction. It's really the energy scale we are looking at the physics is so far below this the vacuum energy. So that is the reason. However, you look at the same ratio energy over the electroweak scale at a very, very high energy. And this ratio can be significantly larger than that. But that is physically relevant because in the electroweak sector, the gate bosons are massive. If the gate bosons are massive, there's the third degree freedom besides the polarization for photons. Photons have only two polarizations, but if once this particle becomes massive, there's an orthogonal state that is longitudinal. The longitudinal wave function necessarily behaves like this, simply by the orthogonality and Lorentz structure. So that is the necessary condition to have this the longitudinal wave function for this massive gate boson. Then that's going to be very sensitive to the high energy regime and so-called the UV ultraviolet energy regime. Once you have the energy with respect to this compared with respect to the energy regime there. So that is the first thing. Let's turn the other way around. If you turn the other way around to think about this, the available energy scale, that's a vacuum expectation value, and in comparison with the possibly higher energy regime. If you think about a high energy regime like 10 TeV, you think about this. This ratio between this, the comparison between the electroweak vacuum is very similar to the dynamical scale in the QCD, and in scale with this the energy regime. You think about the QCD physics around 10 GeV, you start seeing the jazz or this kind of the interesting QCD phenomenology already. But around the multi-TeV, 10 TeV, these ratios are about same. So therefore, we never consider the power corrections to this lambda QCD. We usually call this higher twisting effect. We only consider the logarithmic contribution in the gauge theory. The power counting for here, this is small. This the power correction in QCD due to lambda QCD is small. Therefore, similar phenomena may take place as well. If you think about the multi-TeV, so this ratio is pretty much similar. So in that regard, you may consider this the energy is much larger than whole energy scales. Therefore, W mass is pretty much massless, even top quark mass. If this vacuum expectation value is much smaller than the available energy, and this is essentially the mass theory again. So sometimes we argue this is the reason that electric symmetry is restored. We heard about this word all the time, and the quantitatively what that means, and that was interesting to look into. So therefore, in this high energy regime, even multi-TeV center mass energy, then all the electric scale, electric masses, like even top quark, gate boson mass, it only power corrections to the gauge theory. I think it's kind of interesting. So therefore, similar to the QCD, and these are the V over energy power corrections count for this higher twist effect in QCD. We most of the time ignore the higher twist effect in QCD. Unlike the QCD though, the higher twist QCD basically tells you if the higher twist QCD becomes significant, we are getting into non-perturbative regime. And we are unable to properly do this the power counting. You probably need to use a certain non-perturbative approach, such as light gauge theory and so on and so forth. But unlike that, in the electric sector, above below the vacuum expectation value, it's still perturbative. We know that it's basically perturbative. That you really need to treat these the corrections properly, even in the perturbation theory. You need to do that. So we'll continue on this track. Look at some other numerology. So if we think about the tau quarks is the heaviest particle in the Standard Model, and the B quark sometimes they treat massless. At the temperature, for example, B quark is even safely treated massless already, even at the temperature range. Think about a few hundred GeV this region. 10 TeV high energy, tau quark mass is the same. Tau quark mass can be treated massless. As massless at the bottom quark, at the temperature, if you really want to do the power counting. Therefore, so this is a somewhat different formulation. You can even consider tau quarks as massless and consider tau quark as a possible parton inside the proton, rigorously speaking. But numerically, at LIC it's not relevant yet, by far not relevant. At the future FCC, it may be marginally relevant, but academically, I think that's interesting to look into this to see what we learn. So that is the procedure. So numerically, we can even estimate this the log for the top quark mass times your alpha. That log term is significantly enhanced, and this term may not be too small. So if this is over 10%, maybe small. If it becomes 30, 40, 50%, and this the additional high order terms may need to be resummed to have these concepts such as parton distribution functions and fragmentation functions rather than perturbative single particle production. So that is the energy regime that you may treat this differently. So quantitatively speaking, if you think this log is not small like alpha x, because the enhancement at high energy logarithmic enhancement here, even if you think about 20-30%, then the scale you are talking about multi-TeV becomes relevant already. You need to perform resummation rather than a perturbative single top quark production. So I think that's all. It's interesting. Electroweak logs. If you think of electroweak logs, it's similar to this. Gate bosons will be radiated like crazy. So therefore, the leading order perturbative calculation may not be the leading effect. You may not capture the major physics. Maybe the collinear resummation you should all take into account. Just like multi-gluon radiation. At the LSC, you always need to do the parton distribution function to resum the collinear enhancements due to the splitting functions, and it's similar here. Was discussed in a different context. So similarly, and this Brian Weber's estimate for the scale and versus the log term. The log term can be very sizable. Then you need to resum these to form the exponential, typically the pseudo suppression and the real emission enhancement. So those are the dominant phenomena. Another interesting thing is that in QCD, we think about the color factors. This is the color factor for gate bosons and gluon. This color factor for fermions, splitting, and the ratio of these two color factors to have this gate boson self-interaction versus the fermion interaction is a scale like the ratio is squared over this area. It's slightly more complicated, but the final expression is like that. It so turns out, if you think about A equal to 3 for QCD, that ratio actually is even smaller than A equal to 2, which basically means that just from the SO2 versus the SO3 group theory, at high energies, SO2 gate boson radiation is more significant than QCD. So then SO3. So it's a lot of interesting things that we should take into account to consider the electroweak sector at extremely high energies. So that is another reason. Now I will be rather quick. It so turned out because of that properties, the splitting phenomena dominance. Splitting phenomena have two consequences. One is the inertial state. In this inertial state, you have a lot of radiation, gluon radiation split into quarks, and this we parameterize that into the parton distribution functions. We do the logarithmic evolution, and we call it DGLAB evolution, that inertial state. So you need to do this property, and analogously, we're going to do the electroweak PDFs here. The electroweak gate bosons will behave like partons. That's the one thing we want to discuss. Final state is similar. You have one particle going out, very energetic, like a quark or electron or something. And the dominant phenomenon is not only one particle production. There's no such state. So if the very high energy is infinite number, just like a charged particle with the photon radiation, in reality it's an infinite number of collinear photons around it at a different energy regime. The soft energy has a dominant. This is similar. The splitting function will be dominant phenomenon. You have electroweak shower, electroweak jets to come out in this high energy regime. Of course, you assume the factorization. You assume that the cross-section is factorized into hard process and the splitting. This splitting may be initial state or final state depending on what the observable you look at, and you write down some simple the scaling energy behavior like this, and you go on, and then so I will be quick. On the dimensional ground, this for massive electric theory, then you have additional scale, mass scale. In the massless limit, this is a pure gate theory, almost like a QCD. In QCD scenario, there's no additional mass scale to come in. Quarks, gluons, all treated massless, and this This is how the gauge theory behaves. But if you have the correction, as I mentioned, the electroweak correction, the power counting for this the mass term, the VAC, probably need to be taken into account consistent property, then you have additional mass scale. This behaves very interesting, very differently. So I will show you how this modify the standard gauge theory picture like a QCD. So that's interesting discussion there already. But I want to even bring this up early enough. There's no rigorous factorization like this yet. I mean, it's a process dependent and certain observable dependent. I will show you one particular example. So the factorization theorem doesn't exist. Okay, so even this process dependent and also the scale dependent as well. Okay, so let me be rather quick here. Let's think about the high energy regime. In the high energy regime, we work this at an unbroken phase in the sense that the vacuum exchange value is turned off. So let's say this is set to 0. Then all your physics is parameterized by the gauge sector, SU2 and cross U1, and the scalar sector. So this is the N plus 2 kappa kappa. Then you can work out the splitting functions. And this part is well known. So you have the collinear behavior when the transfer of momentum is close by kt, and you have the soft behavior for this gauge boson. So no matter it's a photon or WZ, it's always have this soft gauge boson splitting behavior. It's very common. We see it all time, even back to the Williams approximation. The leading kernel is like this already. But this is new. You have a scalar, and the scalar flip the chirality. Everything else seems to be straightforward. There's no soft behavior, but there's a collinear behavior. But it's a chirality flipping. This is the chirality notion for this, the errors. So I think that's straightforward. Infrared collinear exists, and this one is the Yukawa interaction to flip the chirality at the leading order. Then we go on to see this the gauge boson splitting. Once again, this is similar to 3 gluons. This is very similar to the gluon splitting here, and this is also similar to QED, QCD, that part. But this part is new gauge boson to split into scalar, to Higgs. Now I want to give you some numerics to show. Particularly, if you calculate gauge boson, multiple gauge boson production, and each additional gauge boson production particularly costs you additional electric coupling and modulate with the phase space. It's almost 100 times smaller. Each additional gauge boson production. This probably would be what you expect at the LSC. Is the perturbative multiple gauge boson production follows the matrix element calculation reasonably well. Even tree level is more or less okay. But you can see each additional gauge boson, you see a suppression almost like factor of 100. However, as I argue, if you go to very, very high energy, 100 TeV or so, then you would consider the possible resummation. There's no very well defined one single gauge boson anymore. You need to resum the collinear behavior. If you include the resum the behavior, that each additional gauge boson, this is the number of gauge boson, and 1 and 2, 3 different gauge boson. Each gauge boson radiation, including the log enhancement here, is only 1 order of magnitude suppressed. This is with I mean it's only 1 order of magnitude suppressed. So therefore, if you include the high energy logarithmic enhancement for this multiple gauge boson productions, and the perturbative picture is not very accurate anymore at very, very high energy.
So, Tao, just to make sure I'm understanding, in QCD and colliders, we have a sort of rule of thumb that anytime you have a quark or gluon line, there's about a 20% chance it will spit off another gluon, right?
Yeah.
Looks like that's about the same for
Similar.
the number of W's or Z's
Yeah.
split in that bottom plot.
Yeah, so that's exactly the same picture as long as the log enhancement is similar. At the low end is QCD. The log term is measured with respect to dynamical scale lambda QCD. It's very, very low. So therefore, even 10 GeV, the 100 GeV, you have this picture as you said already. But here, it's measured with respect to the electroweak value.
But here you say each W costs you a factor of 100.
This is a perturbative calculation from MATLAB, for example. This is what the MATLAB will give you. I'm arguing that if you go to a very high energy, this matter graph perturbative calculation is not accurate anymore because of you have additional log enhancement. It's more inclusive, somewhat more inclusive than. So those are the ones including the log correction terms. So this is more similar to what your picture say that you additional additional gluon radiation will cost you only it gives you 20% chance you will see that one. I said 10% chance you have additional boson rather than the perturbative electric coupling. So that is one. Then numerically, I can show you that the implementation I said there even does not exist in the current generators. If you look at the P-theta doesn't have it because of the collinear 3W boson self-interaction, including the collinear behavior, that doesn't exist. So this is the plot from matter graph. We look at the W pair plus one jet. Okay, so here is a Z and jet production with collinear radiation W in this region. So the separation between W and Z is near pi. Okay, so this is the pi. Here, this is the W production and a jet, and with the Z collinear radiation. And this is here. So this is also pi, and the P relative to PT here is a high. PT between these two. Okay. Now this region is new. This is a jet against a gate boson, but that's a split. This term, in terms of resummation, doesn't exist in any generators. So this, so in terms of the collinear, particularly that term is there in the math graph. Anything you can calculate.
In math graph, is it properly resummed?
No. But math graph has no resummation with the formula I showed you. It only exists in theory.
So what are we going to do?
Well, at the LHC, it doesn't matter very much. But if you go to FCC, you must implement this for sure. So let me show you this numerical result. Here is a P-theta output. P-theta has this piece with a Z and the jet. That's it. P-theta has a W and Z, but the collinear, large collinear enhancement from this gate boson scattering doesn't exist. This is P-theta output. You just simply run P-theta and to look at this particular angular distributions and the region that doesn't exist. This one is what we are our estimation. It's more or less similar to the math graph, but our numerical result we have a somewhat bigger result.
So
Yes.
how hard technically is it to add this to Pythia?
So you need to have this the showering to change the P-theta showering. P-theta showering is basically a billion. I think 2 years ago, Xiuchuan added one electric piece. It was in a paper. He said I added one more piece, but that's incomplete yet. You need to change the electric showering.
Yeah.
So the P-theta certainly has showering, as we know, the gluons in the consistent way, but it doesn't exist.
So right now we generate our hard processes with MadGraph and then send it to Pythia for showering. Will we have to do electroweak showering in the future?
Yeah, exactly. That's the correct way. So you need to do this. Otherwise, you miss the self-interaction. You miss this collinear term. Now, if you simply run the Pythia at this high energy 100 TeV FCC HH, this the collinear splitting in the electric sector is not implemented anywhere. Not only Pythia anywhere. The math graph is perturbative. Pythia has showering only in QC. Maybe QED is not in any way. QED doesn't really give you this feature. For example, I'm trying to emphasize that some new implementation will be needed if you go to 10 TeV partonic 75%. So I think that's one thing. And so let's go to the next one. I want to comment on the Goldstone-boson Equivalence Theorem somewhat. I think this is also an interesting part. Long time ago, of course, even the Lee Pythagoras, the famous paper to argue about the unitarity, where the Higgs should show up, where the energy cutoff need to be to restore the electric unitarity. That was the argument. At high energy, and the electric sector is separated from the gate sector and the scalar sector. That is the equivalent, Goldstone-boson Equivalence Theorem. But that is straightforward. Let's go back to the broken phase and write down the longitudinal wave function. That is proportional to this. Let's scalarize this. Multiply this vector into your currents. and you have no vector anymore. And that is how you derive the Goldstone-boson interactions. So then after you replace this one, and this one reproduce the Goldstone-boson interactions plus the higher order fractions. You assume this energy is high, this fraction is small, and you drop it. Then somewhat you run into trouble. Before that, I want to comment on the physical significance. Physical significance means that if you scalarize your process, let's scalarize our process for the heavy fermion, initially to gate-boson pairs. And then if you look at the longitudinal component, these had a very bad high energy behavior. This one is proportional to energy, this one proportional energy. The amplitude with proportional energy squared. But if you include all the gate vertices, then the gate boson can be radiated here, can be radiated here, and can be radiated here. You include all the diagrams, and so there's a big cancellation. So the amplitude will be proportional to the energy linearly rather than quadratically. Okay, so that is the statement. But this is still bad energy behavior. What happens is that you need to have this Goldstone-boson structure, including Higgs. Higgs is one of the 4 components in the doublet. So you include Higgs then. This is kind of your Kappa equivalent, and you include this Higgs here, then this bad energy behavior is cured and replaced by the Higgs mass. So this is the proper standard model prediction. And that's why the Higgs is so important, so good. Higgs is very light, relatively light, narrow, and then the standard model behavior gives you very predictable good energy behavior. However, if the any modifications that take place, this cancellation will be incomplete, and this will be sensitive to the higher energy UV physics if you look into the longitudinal components. Otherwise, in other words, you look into the Goldstone-boson interactions. So that we did. And of course, Jack and I worked on this long time ago for this WW scattering or not, for that same reason. So now this is the one thing. However, let me continue on this argument. Let's scalarize your longitudinal gate boson. You scalarize this longitudinal gate boson, you dump this into your current. Let's dump into this fermion current. You have a quarks, and very light quarks, massless quarks, to radiate the longitudinal gate boson. And you replace this by this scalarization scheme. Then you look at this fermion radiate this one, and because of this the partial conservation of current, this becomes proportional to the fermion mass. That is the statement of Goldstone-boson Equivalence Theorem. Goldstone-boson Equivalence Theorem said at very high energies, and this should be scalarized and give you the Goldstone-boson. But this proportional to the fermion mass and the proportional to your carbon is 0. That means the fermion will not radiate longitudinal gate boson, which is wrong. You observed that already. VBF and the Higgs. So what is the situation? This is the first manifestation that this is Goldstone-boson Equivalence Theorem is naively violated. In fact, it's not violated in the sense that because you ignore this term. This term turned out to be dominant term. Higher twist, electric physics, dominance over than your predictive calculation. So that's why we said this proper power counting. You need to look into this consistently if you deal with the high energies, not simply saying that the trivial statement to say you replace longitudinal by the Goldstone-boson, that is the theory. So this term, the higher twist effect in the electric sector becomes the dominant contribution rather than your standard coupling, the Yukawa coupling. Only until you go to top quark and this form. So therefore, this is true. Then of course, this first demonstrated by these 2 papers, Gordy and Sally. They calculate this splitting, fermion splitting into a fermion ungate in the longitudinal gate boson. The transverse gate boson will show you already. This pretty much works like a Williams approximation in the electroweak interactions. But if you look at the longitudinal component, this logarithmic term doesn't exist. But it's not 0. It's not 0, but this doesn't exist. What is going on? We'll continue for this feature. So of course, this is the reality, and this exists and has been observed. And you simply cannot ignore the longitudinal component in order to get this the Higgs discovery rate. That's true. So what is happening is that you need to you need to consider the high order, not the second term corrections, not the collinear law. Collinear law doesn't exist in this the longitudinal radiation. So this is what we calculate. That reason is because of additional scale. In QCD, this scale, lambda QCD doesn't contribute. It's a higher twist effect. We drop them all. Okay, and then the electroweak, even below that scale, that's physically exists. So then you have to consider this correction because of the new scale. The line correction, you take the integration over there, is not the log. Here, this will be the log, but then you have an additional factor here, and that factor dominance, and then in fact you have this one. We call this the super collinear effect. So there's a power suppression for this diffusion. Anything beyond this the high PT is cut off. Only within almost like step function, and you have this the diffusions. And this is what we observe. So this is the one that Sally and Gordy company calculated in the 80s. So this is the leading one, and you find that all the other the Higgs radiation and the longitudinal radiation will be similar to that. Or you have incredible projects. So this is that you so let me skip out all the detailed discussions. The point is that the leading contribution for the longitudinal radiation is not the same as the Goldstone-boson Equivalence Theorem set. Because Goldstone-boson Equivalence Theorem set is Goldstone-boson coupling is your couple coupling is 0. But the largest contribution is really from the higher twist electric symmetry breaking effect. We are counting for the electric symmetry breaking. Okay. Either in the purely symmetric phase or the low energy phase, but somewhere between this, but the power counting needs to be treated consistently properly. So this is what the point there. Okay, so then I calculate the process. Let me be quick, so skip this observation. So this is the kind of summary. We call this ultra-collinear behavior because of this the existence of the scale. We need to treat the scale. Okay? When the energy is transfer the momentum energy is larger than that, it's shut off. It's almost like the step function. Inside here, almost like flat. So this the Goldstone-boson radiation of that is very collinear. It's interesting that okay, so this is in numerics. You can see massless gauge boson is very much like a photon and a gluon. This was typical case versus a transfer momentum. Once you have the mass, it's regularized around the W mass. It's similar, but longitudinal. It's only happen to be in this the step function inside here. So that's why we call this the ultra-collinear behavior. So in fact, this a long time ago when Jack and I we were working on this VBX, we observed this phenomenon, but this is the best explanation for that. We invented this so-called 4J tagging and the central jet vetoing. That was because of this, actually. So you see that if you think about it, the longitudinal sector, the Higgs sector, the transfer the momentum for this jet kicked by this is not very high. It's half of W mass or so. So you want to tag the jet in the relative forward region. It's not a central region. It's mostly transverse gauge boson. So in the central region, you hope not to see this. You veto the additional gauge bosons, so you can focus for the longitudinal interactions. So that was this started in the 80s. The terminology basically came out from this kind of study. But now we seem to understand more quantitatively exactly how the power counting gives you these the features. So that was the early time.
Just a minor question are you using the mass of the W and the VEV kind of interchangeably, or?
Yeah.
Okay.
Yeah. So once you couple to the current, you pick up the G squared, and over W mass it gives you the VEV. So basically, the VEV is the VEV times G is a W. So once you include the coupling to the current, it comes to the same thing. Like G Fermi, the Fermi interaction, the full-point interaction. You don't need to introduce W mass or coupling.
Right.
At the very end, really the scale sets how fast, how the decay is. I use this interchangeably, but if you put everything together, you can see this is there's a consistent picture. Okay, So now, that is interesting. We can ask the longitudinal anti-transverse gate-boson radiation the probability. So this is a fragmentation function for a particle I to fragment into a W. So therefore, because of the high energy enhancement, longevity enhancement, quark would give you a significant fraction to radiate a W. That's why in the high energy electric sector, a quark is similar to the QCD quark. Quark is not an isolated quark. Quark is associated with a bunch of gluon radiations. It's a kind of a jets. This is almost like electroweak jets. So you have a huge probability for quark and lepton. These lepton includes any electric particles, such as an electron and neutrino. Neutrinos is not missing energy anymore at this high energy. Neutrino will radiate the W and Z and like a crazy in a couple of them. You have electric jets. It's a certain probability that the charged lepton and neutrino will radiate a W. This is the W production from this fragmentation. So the lepton neutrino will have the WZ component inside the original particle jets. So basically, you're talking about electric jets. Neutrinos will radiate at the high energy. Neutrinos not missing energy. Certain fraction, easily 10-20% probability, neutrino will end up having this the W radiation or Z radiation at the high energy. It's not surprising. The same as the QCD, except you scale up the scale by 1 TeV. I think that's interesting. Now this part is interesting that I think I want to point out to theories. There's an incomplete cancellation here. Remember, if you learn field theory, you have this Lie number kinetic theorem to say if you sum over all degenerate states in the softer photon radiation, the finite cross section is always the final results are always finite because of the cancellation. If you resum all these things. But there's a subtlety here. So let's look at this the high order fractions. If you look at this the electron, it plus a softer gate-boson radiation, then the softer W radiation in principle presents the soft and the collinear singularity, just like a photon. You need to have this one-loop correction to come along together and to have this the possible cancellation. So therefore, you want to include the one-loop correction in the same soft limit to see the cancellation. This is how it works for this the QED and QED theorem. But you don't have this here because it's final state is neutrino. This final state is electron. Once you close the loop, they are different particles. They don't interfere. You don't have the cancellation the same way. So this is a new twist. So this is incomplete cancellation. For this, the reason is the theorem said you need to sum over all degenerate states. The reason is that the flavor experimentally is observable. Electron neutrino experimentally is different. But in the QCD, color is never observable. You always sum over color. Okay? So once you sum over all these gauge quantum numbers, then here in principle, you should sum over gauge quantum numbers. You should sum over the gauge doublet. You should need to sum over these two terms. Not only the electron-neutrino conversion and neutrino-electron conversion, also need the electron-electron neutrino to do four of them in the same equal footing, the isotope doublets. You need to sum over them. If you sum over them, then that is cancelled by the one-loop correction. Just sum over all these things. That is sufficiently inclusive. That basically means that neutrino, once again, neutrino is not always, rigorously speaking, neutrino is not a well-defined quantity anymore at high energies. Neutrinos can easily change to W with a 0 with 100% probability if this is soft, the W radiation is soft. So you need to, so that is also interesting aspect that the fragmentation I mentioned, the PDFs, fragmentation functions depends on this how inclusive you are talking about. So I think that's also interesting aspect. So this is called the violation of the Bloch-Nordsieck theorem. Bloch-Nordsieck theorem is, I think, in the 30s. They point out how to cancel these soft singularities by summing over all these degenerate states. But here, if you demand the identification of electron flavor versus neutrino flavor, you are breaking the ISO2 gate quantum numbers. You need to sum over all the ISO gate quantum numbers to have this proper order by order cancellations. So this has not been rigorously worked out. But nowadays, what we did is, let's introduce a cutoff W mass. W mass exists anyway. Once you introduce W mass, you don't hit singularity, but you don't have the accurate prediction. Your prediction is more or less fine, and 20-30%, but you don't have a better prediction than 20-30% if you don't deal with this the factorization property. Unlike QCD. QCD factorization exists already. Of course, it's also process dependent. The major processes we show, Sturman, Colin, and John Collins, and Soper. So they showed how to properly factorize these things like this. And in the electric sector, these kind of proper treatments to that accuracy, treatments still don't exist yet. But we know more or less the correction. We know more or less how to go and where to go. Okay, so now, so much for the theory aspect. I think it's interesting. I'll continue to look into this. It's somewhat more academic, but not quite immediately relevant yet. We don't have multi-TeV collider for the next 10, 20 years. But I think this the question remains to be interesting to explore how to see this the scalar sector versus the gate sector in connection between longitudinal gate bosons. They have a different power counting. You need to treat them properly. Now let's look into the possible application to multi-TeV collider. That's I think that's generally a lot of excitement. At the early time, even almost like 30 years ago, there was some comment about the possible muon collider construction. But nowadays, probably the most challenging is about cooling to make this muon beam in such a short lifetime. Of course, at the rest, it's microsecond, 2.2 microsecond mu c, microsecond, 10⁻⁶ second. So then, if you accelerate the muons to a high energy, you gain this gamma factor. So that you can gain the gamma factor easily 10 to the 5th or something, right? So in that case, then the muons will be somewhat much longer lived, long-lived, so that you can hope to accelerate really quick, put them into the storage ring and accelerate them, and then collide them. So that was the concept. Every stage is challenging. You have a large number of protons on target to produce a large number of pions and the kaons. And the pions and kaons will decay into the muons in all directions. Okay. Then you have to collect them all together to cool down. It's called to cool down the 6 dimensions. 6 dimensions in a sense of momentum and space and time. Cool them into one direction, let go. So that is very challenging. The cooling stage is most challenging. It was thought impossible for a long time. And then acceleration technology is so advanced, it's not a big deal. Once you collect the beam, you can accelerate it within the 100 meters to a few hundred meters to move these muons as fast as the TeV, few hundred GeV. So that was from our accelerator colleagues' claim. The acceleration is not the bottleneck. The beam quality is the bottleneck. For a long time it was like that. But then you can consider to accelerate the muon to a significant energy to perform the collision. So a couple of years ago, in 2019, and of course, after last P5 canceled this, we know that we were extremely sad. And the last P5 canceled the muon R&D program at the Fermilab and basically eliminate all the project. And then the project, the MAP, the muon accelerator program moved to Rutherford Lab, and they set up a new what do you call this? Muon ionization cooling experiment. I think that's nice. Moved from Fermilab to Rutherford Lab. In 2019, they demonstrate the cooling effect. They have initial beam, then they go through some materials and to absorb all these momentum in different directions and let them go. They reach something like between 10 to 20% the cooling effect. And that was interesting. It was exciting, but by far not enough. 10-20%. You need to have a 90% power to reach this. You need 10 to the 5th. You need to improve this by 10 to the 5th. so 10 to the 5th, to have a quality beam. So, but nevertheless, this demonstration showed, well, that's not totally impossible. This is one step. You can do many steps, a few hundred steps within 100 meters or something. So they claimed there was a lot of challenges, a lot of demonstration need to be done. There was no demonstrator. In fact, these P5 support this. I will comment on the P5 segment. So they basically asked for a demonstrator at the Fermi-lab. So if they can demonstrate a few steps further than this, and not the isolated muons have a bunch of muons, that probably will show the community that how far we can go, how far we cannot go. But that so far, honestly, doesn't exist. Technology doesn't exist. But this one showed a lot of excitement, in particular our young generation. So Carrie was very verbal, and she was a junior faculty at Chicago. She went to CERN for a visit, and then the CERN courier interviewed her, and she said, we cannot wait for future colliders. And she will make big statements, somewhat even controversial statements. And nevertheless, the young generation, we think it was interesting. And assuming the technological challenge can be overcome, muon collider would be the attraction. Even rather recently, I think it was August last year, and Scientific American carried another article to say the particle physics is dream for muon collider. And of course, it all came from many studies. In fact, I want to quickly comment on this thing. Almost like 30 years ago, and Jack and I, and the Barber and Berger, we called ourselves a muon quartet. Only 4 of us. Almost in the world. Is that true, Jack? Only 4 of us think about this. Of course, crazy. We did not know it's doable or not. But it's interesting to think about the possible physics consequence. So we, of course, we wrote the PRL paper and the physics report, and to argue the possibility to build a Higgs factory, sitting on the new pop muons, the resonance at the Higgs 125 TeV. Even before the 125 TeV was discovered, we used 120 TeV, very close, right? It's only a few percent off. So we used that demonstration that this was a good need. However, this is the disfavored argument. The Higgs is so narrow. Higgs is 5 MeV. If you want to have a significant resonance signature, you need to have the 100 GeV beam energy and 10 to the minus 5 energy spread. That's durable. It's much better than E plus mu. E plus 1 is reach about 10 to minus 3. At lab, is that true, John? The 10 to minus 3 lab, you can reach
Beam energy spread.
Yeah. At lab.
It's quite small.
I think it's 10 to minus 3 or so. Maybe 10 to minus 4. But this is significantly better than it might E plus minus. Because you have this the procession to tune the energy, so you can improve by order of magnitude or maybe more. So it's not impossible, but you put additional constraint on your cooling. You select much less event, more restrictive to do Higgs factory. Because of the energy frontier, these new high energy options seem to take over nowadays. People talk about the Higgs factory much less, okay, and partly because we have learned so much about the Higgs from the LSE and maybe the next generation, the Higgs factory. But now the scaling for the high energy, multi-TeV high energy takes over at the energy frontier. I think that's a part of the excitement. Of course, you need a high luminosity to compensate this the behavior. Typically, the cross section, the discovery cross section is like 1/s, the pair production cross section. You want to compensate on that, so you want to also have a S dependence, which turned out to be possible. The reason is once again only for the muon collider. The more the boost you have, the longer lived the muons would be, and the larger luminosity. It's the luminosity scale with energy. You gain, unlike the other things, you gain with the luminosity. More particles will get into the scattering. So this is possible. So the current choice, the 3 TeV to compare with the click. 10 TeV is a 10 TeV parton center mass energy, and it was claimed up to 10 TeV or so, you may be able to handle the current difficulties such as the neutrino hazard and quite a few additional complications. And our accelerator colleagues seem to claim that you have some ways to handle up to this energy. So that was it. So at the SNOMAS, we tried very hard to think about the energy frontier, and then this is the SNOMAS report. SNOMAS report said the muon collider remained to be a highly appealing option for the US. and it's complementary to the Higgs factor. And then, of course, with even some kind of a timeline to argue that how long we are going to 10 years or so we are able to develop the R&D, and maybe 15 years or so we probably can start the possible construction. Of course, this is the optimistic scenario, and the other possibility is backup for the ILC. And our SLAC colleagues at the SLAC want to do a cool copper collider and to basically do the Higgs factor and around the 240 GeV. So those are the possible options that we may jump into rather quick. So that was the Snowmass report. And we are pleasantly surprised to receive this very strong support from P5. So this is a P5 statement. P5 said the realization of the future collider requires resources that the long-term ambition for hosting a major international collider in the US is in a global effort is a high priority for us. And then they continue on to say a muon collider presents an attractive option, both technological innovation and bring all this energy frontier together, and that will be able to reach 10 TeV partonic synchronous energy. And then it goes on. We do not know the muon collider is ultimately possible, feasible yet. So, but this is our shot. This is on the moon shot. So they made this such a catchy name. And then last week, Friday, Thursday, there was a science article to even carry the same topic. Quite a few of our colleagues were interviewed there. So last week, the science article was muon shot. So I think that's interesting. The point is that generally a lot of excitement among our young colleagues. I think that's make the field dynamic, and we continue on to think about the physics still long term, and technologically it's new. So the new technology will have a spin-off and may have something to do with neutron physics and so on and so forth along the way. I think that's a interesting. When did I start? Did I start at 4?
No, started at 4:15.
4:50. Okay. So let me be rather quick. Okay. Now the important point is that at such high energies, the charged particles like muons are not always annihilated directly into each other. In fact, the probability for them to directly annihilate is very small because the cross section is inversely proportional to energy squared. It's suppressed. Unless you reach the threshold. Once you reach the threshold, you open the new threshold. That's different. That's a new physical discovery. Normally, it's not. Normally, as I argued, the splitting phenomenon dominates. So, in fact, the parton concept, if you think that you be as the partons inside a proton, which was the original idea, but dynamically, this is not the very well-defined concept at high energy quantum mechanics. Why there are gluons? Gluons do not contribute much about the vacuum quantum number. Why you call the gluons? Why you have BBX? Everything is a parton, dynamically, quantum mechanically. So at high energies, everything is radiated around, everything can be generated. This is everything is parton inside anything. There's no elementary particle. And at high energies, electron will have radiation around this. Anyways, a lot of photons radiate around anyway. You can calculate the probability of finding some energy photons in a highly energetic electron beam. For the same concept, you can find quarks, gluons at high orders from this splitting function. So therefore, you really need to couple all these standard model particles, quarks, photons, gluons, and everything else into this evolution function, this generalized Dirac equation. So in QCD it's well defined, but we argue that because of the interactions, electric interaction, electromagnetic interactions, any particle should be viewed as a parent to generate a dynamical partons inside. So therefore you couple these all together, and then they so turn out to be, and so you have different scale. In the QCD scale, you only do QCD. When you move on to the high scale, you turn on the new threshold, and the electric gate boson become essentially massless. They all contribute as partons. So this is the one interesting. Now we calculate these things. So here is the parton distribution function versus the energy fraction. Here is the muon radiation of the gate boson, neutral gate boson, the gamma Z. Gamma, of course, the mass case is the largest. then you can radiate the gate, the transverse polarized gate boson, and you can even generate a dynamic generator quarks, and you can even generate the dynamic gluons. We wrote the paper, the gluon contents inside the electron. This is a dynamic process. They all exist. So in principle, of course, you pay for the coupling, you pay everything, but in principle, they all exist. The only two valence particles, one is the original muon. Original muon carries the full energy, of course. This radiation is soft. So this is the full energy from the original muon. So, but there is a radiation tail there. But neutrino is a valence because the neutrino is coming from a soft W, very soft, massless soft W radiation. It changes flavor from a muon to neutrino. So this is the muon. This is neutrino collider. You have neutrino carry full energy with a soft W radiation. So that's a dynamical process. It's really calculable. Then we calculate the parton luminosity. This is the same parton luminosity as everybody using the LSC. The particle Ij as a sub-process, as a partonic cross-section, convoluted with this, and this with the gamma fusion. This is transverse W fusion. This longitudinal W fusion. This is the partonic luminosity for that. So therefore, in principle, you have valence Newman annihilation. You have neutrino annihilation. Those are the high energy regime. Those are the new particle discovery range, and this is the general range. So I want to repeat. So the valence particles left and right, muons as well as the neutrino from soft radiation, soft gate boson radiation. Then those are the ones that quarks and next leading order gluons exist, and then next leading order because the two-level splitting, everything exists. Q2 bar exists in the muon collider. Gluon diffusion exists in muon collider. Of course, high order. So this is dynamic. So I think this once again academically interesting. Numerically, whether it's significant for discovery, it's hard to tell. But then this is the typical 1/S annihilation cross section. Those are the logarithmic VDF parton scattering cross section. By far, if you look at the Higgs production, by far the VDF dominant by order the magnitude. Then you make Higgs pair production and so on. So that's interesting. The interesting point is not only this one has these two features, we can even separate them out. So the direct annihilation focus on the emergent mass, very similar to the machine center mass energy. But the radiation is taken away in the relatively low energy region. So you can look at the emergent mass of the final space system. And this is similar. So the direct annihilation will have no transverse longitudinal hit, longitudinal boost. It's more in the central region. But the VBFs, just like the LSC, spread out. So from this rapidity spreading distribution and the emergent distribution, you may be able to separate even the same final state from the VBF contribution and direct annihilation. So to some extent, I call this the muon collider is by one gate one free. You have both features. Leptonic collider to directly annihilate to reach the new particle threshold, or the VBFs from the large radiations, similar to the LSC. So I think that's also interesting, pretty cool. So let me see, am I running out of time? I only show some comparison for the different results. This is a high luminosity LSC for the colored SUSY particle searches, and then LSC by far it's very good because it's colored production mechanism from the gluons. For star and Reno and LSC, and the future collider will take very far away. And this is essentially only at the threshold. 10 TeV machine, you can read 5 TeV, that's it. However, if you look at the electroweak gate sector, the LSC had a hard time. We know that the electroweak keynotes, and it's very, very hard. Production is not moderate, and the identification is hard against the background. But muon collider will take all the way to the threshold again. So that is very important. And if you run a quick Higgs production, you have 10 times more than Higgs factory because of a larger cross section. And so you have an order of 10 million Higgs from the VBS. So the Higgs factory is at 1 million. Higgs target for the whole lifetime, the Higgs factory is 1 million. So you can reach 1 over 1 part of mil accuracy, 10⁻³ accuracy. That's the Higgs factory target. But this one you have because the fusion process is much bigger, and you have an order of almost a million Higgs pair. This will be the very important thing to measure the triple Higgs coupling, and the LHC will have a hard time. To see the Higgs pair production is an achievement already, but to measure this triple coupling is a small piece of the Higgs pair production. You probably can reach the order of 50%-ish, but it's not as accurate as we would like to see. If you go to the FCC HH, you are at a few percent level. A few percent level will be relatively conclusive to say the Higgs potential standard model is basically right, and that tells you the electric phase transition probably is a crossover phase change rather than the sharp phase transition. It has a lot of very, very important cosmological and the other consequences, such as the electric biogenesis and so on and so forth. So measuring the triple Higgs coupling tells you the third term in the Higgs potential, and only until you reach this level, the LHC is not going to answer this in a conclusive way. So here is where you really see the fine structure for this Higgs cell interaction. I think that's almost the end, but one more point is also interesting. In LHC, you always do missing energy. So in fact, you only do missing kinetic energy. Missing mass is the information doesn't exist in LHC because of the unknown longitudinal boost. But here, like particle collider, you can define the missing mass by all the observable particles. Initial state, final state, well, how many particles you have, fine. Just sum them over here and take the emergent mass. That gives you the missing particle mass. So here is a missing mass distribution for the particle collider. If you have a 1 TeV missing particle, even missing, not measuring that, you know there's a cutoff from this. But this information doesn't exist in the hadron collider because you only look at the kinetic missing energy, not the total energy including mass. So that is very cool. Then you will be able to do a lot better in terms of the dark matter search. So then here is a comparison. You can cover the so-called thermal radius density range for Higgsino and Higgsino, Higgsino, as well as arbitrarily high representations. So I think that's probably, yeah, let's see. I think that's interesting both academically and possibly practically in the future to think about the electric sector at a very, very high energies. In fact, when I was a kid, a UTB kid, when I was a postdoc at the Formulab, I talked to Chris Quick. So what is interesting that Chris Quick said electric physics at a high energy. I said, I thought you wrote paper already. Didn't you write this the Higgs math? He said, it's still not done. Think about the electric physics at extremely high energy. I think that's academically interesting. You see quite a few features. Of course, in the hope that this will be applicable to the multi-TeV center mass energy machines, like the hadronic and multi-TeV collider. And in fact, this is very relevant too, the high energy cosmic rays. And the multi-TeV center mass energy studies are achievable already. You may want to see these things along this line as well. So still interesting theoretical and practical issues to think about for the electric sector, including the pure gauge and the scalar and somewhere between. And I think it's still fun to look into that. Let me stop here. Sorry to run over time.
One question, I'm sure you said, but at the muon
2 to 3%, yeah, between 5 to 2% is. Yeah.
and what about the CCC or whatever you want to call it?
Oh, this the Higgs factory.
Yeah.
That's very far. That's 20%. So because you don't have this energy produced Higgs pair yet.
Yeah.
So you need at least the ILC at 1 TeV to even accessible to this the Higgs pair production.
And if you had the ILC, what percentage?
ILC is the same. It's a virtual effect, and the loop effect or something, and it's not direct production. There's no direct pair production. The loop effect and the considered contribution is something like 30–40%. Is not much improvement over LHC. Higgs factory cannot do triple Higgs coupling. You need to go to high energy to produce Higgs pair.
Yeah.
So that's why this one this opening a new kinematic regime.
So you have to have a muon collider, in other words, in order to
We
really
must have it.
know if
Yeah.
electrical symmetry
We must have it. Yeah.
works the way we think.
The FCC HS may reach some similar sensitivity. because of the energy and also the large number for production.
Yeah.
The Hadron Collider is a Higgs factory. So now the LHC produced what, the 10, 30 million Higgs already, way beyond the Higgs factory expected. But the reconstruction efficiency is very low, you know. So when Jack proposed the gamma mode and the tau mode, those were 10⁻³ at the beginning, people did not believe him, but it's 10⁻³ branch refraction. What you are talking about? It turned out to be the efficient way. And, so it's the very low efficiency but clean.
Yeah.
The gamma turned out to be the discovery channel at the beginning. So typically 10⁻³ efficiency.
Yeah.
So for the muon PDF, I still don't understand why there's a peak for neutrino at x equals 1.
Oh, yeah. So if you think about the muon beam coming into here, so as I said, at high energies, they have a lot of radiation, photons and this anyway, right? So when you reach the collision, this muon energy is not exactly the same as this one anymore, but the radiation is soft. Radiation is soft, this one is not a delta function as original energy anymore, but very close because the radiation is very soft. The energy to be carried away is very, very soft. Okay, that's the typical situation. Neutrinos are similar. This one radiates gamma a lot. This one radiates W, and high energy W is all same as gamma. But here you have a W radiation. This is soft W. The soft W carries zero energy. That's where the peak is. The peak is this neutrino energy here. It's pretty much same as this original one because of soft radiation. The radiation, the muon has a lot of radiations, including W radiation. If the muon radiates a W, it's converted into the neutrino. So that's a neutrino factor. It's a neutrino collider. Like E plus minus, mu plus muon collider here. You never call this, this is different from that muon. You have a lot of radiation too. You can model this radiation. They call it initial state radiation, ESR, initial state radiation, ISR. Initial state radiation, you have a lot of these. You model this, and if you want to do accurate calculation, you really need to model this to use this new energy distribution for this one to collide. In a sense, this is the parton, I call this. This is the parton inside itself, inside the muon, after the radiation. Everything is a parton. WC is all parton. Everything is parton dynamically. I think this is correct quantum mechanical concept rather than seeing the intrinsic particle inside the particle. That's not the dominant feature. Any elementary particle is parent to dynamically generate all the other particles at high energies. You can even predict.
It's like keep radiating W, so it's switching between muon.
Right. So therefore, the neutrino flavor is not well defined in that sense. That's why you need to sum over this the quantum degenerate quantum numbers to have well-defined quantity. It's kind of jazz, electroweak jazz, similar to quarks. Think about the quark analog. Quark color is not well defined. The quark color, red color coming in, the radiated gluon change color. Another gluon is split into gluon. When you observe this in their the hadronic colorimeter, it's a bunch of particles, the jazz. You have an effective sum all these gauge quantum numbers in the particle. They are already. So in that same sense, neutrino is not well defined quantum number. Neutrinos is associated with a lot of radiations and up being in your detector of all the possible particles.
Can we use this to test the existence of right-handed neutrino, like extra color?
That's an interesting question. But so far, all these radiations are within the standard model, right? Within the standard model, it is the coupling is well defined, left-handed. Right-hand neutrino, I think you probably need to do different measurements. I think the best measurement, which is also model dependent, is the neutrino order double beta decay. So I hope that this neutrino is Majorana. That's absolutely conclusive. In fact, that's probably so far the only way to measure not only way, second way to measure the neutrino absolute mass. So the endpoint is one way to measure the neutrino absolute mass. In Majorana neutrino, the Majorana mass insertion in the middle is proportional to the mass, not mass difference, unlike the oscillation experiments.
Any other questions?
So I'm still a little confused. If you have an ultra high energy neutrino cosmic ray entering material like ice, would it not then emit a W and become a charged
I think it would.
lepton and shower and give us much larger signals? Or
I think it would. So I think there was a paper by Christian Bauer to put some bound. There was a paper by Christian Bauer to put some bound on that. And it was so far does not seem to generate a large enough effect yet.
I see. But in principle, it's there.
Yeah.
And,
Yeah. What is the junior faculty's name or drive in the LBL?
Oh, Nick Rod?
Yeah, he co-authored with he is an astroparticle physicist. Christian Bauer was the electric guy who worked on this, and he wrote the joint paper along this line maybe 2 years ago. And it was exactly the same idea to say you develop electric shower when you have neutrinos, other things, and what that effect would be. I forgot. It was kind of a bound, not very significant yet. Yes, there will be effect at some point if you have the accuracy to collect the showers. I think they will have this. But this is general prediction. There's not something, not new physics.
Right.
It's predictable the probability for certain distributions.
All right, let's thank Tao again.